thanks for the organization, for the inviting to this very nice and interesting meeting. I'm sorry not to be an historian, but I'll try to reconstruct, according to my knowledge, the history of deterministic chaos and its development since the discovery by Henri Poincaré till today, till the birth of the science of complexity. So, this is a short summary of what I will try to say, although I will for sure not be able to finish. And I will start to ask myself and you why there are so many deterministic laws in science which have no real possibility of prediction, like the motion of a ball inside a roulette, the motion of a falling feather, earthquakes, and so on and so forth. And why this seems to be dominated by chance. Actually, there are for sure deterministic laws, but we say that this is just dominated by chance, at least up to now. Well, Laplace was quite clear in this statement. He said that, as you probably know, all of you know, that an intelligence that would know the law of nature and could be able to develop, to solve this equation, could predict the future and the past. And this was actually true, but it didn't mention that in order to solve this question, you should know also the initial conditions. And this was realized by Poincaré. It was published in his famous book, Science and Method, in 1908, in which he realized that trying to solve the three-body problem, that this had no analytic solution, and actually that if you don't know exactly the initial conditions, then it's not possible to predict the future or the past, and small difference in the initial condition could produce very large differences in the final phenomenon. This was when Poincaré participated into this competition by the King of Sweden and Norway, Oscar II, realized this important fact, but actually he was a pioneer, he was very clever, this gave him a lot of recognition, but it was too in advance for his times, and so this thing was also, because it was very difficult to study this kind of phenomena, was more or less abandoned. A few things about determinism and predictability, because when we start at school, we believe that determinism and predictability are almost the same thing, but actually, due to the fact that simple nonlinear laws can have a very unpredictable behavior, these two are not the same, and we should distinguish. And this is also a lesson, because we could have very simple models with nonlinear dynamics, which could have a very complicated behavior, so you don't need a very complicated model in order to describe reality. And it is very easy to show that. Imagine, in order to have deterministic chaos, which seems an oxymoron, it's just you should have an exponential dependence on the initial condition with an exponent, which is the Lyapunov exponent, which is positive. So imagine that you find a phenomenon which is regulated by this uncertainty which grows exponentially, and then imagine that at a certain point when this uncertainty is too big, of the order of 1, you invert that equation, and you just calculate the maximum time that you could predict your behavior until this uncertainty reach the value of 1. Then this is easily calculated, and due to the fact that you have a logarithmic dependence, you see that even if this Lyapunov exponent, which should be positive, of course, is very, very small, in order to double your precision, your maximum time, you need to diminish by orders of magnitude your precision. And this is the essence of deterministic chaos. When you have such an exponential dependence, it's not important maybe you can predict your evolution up to a certain time, but there is a limit. There is a limit which is due to the limitation of computers or the limitation of your experimental possibilities. So this is the essence of deterministic chaos, which was realized by Poincaré. And actually, as many things in science, deterministic chaos was neglected for so long, but it's almost everywhere around us. But if we don't have very often the instruments to see what happens around you, you don't see things. And this is a lesson for young people here in the room. So it's very common. You have it in billiards due to the focusing power of circle obstacles, and these are geometric solutions, so there is no error in it. And it was realized by this mathematician, Robert May, in 1976, with a very simple map, the logistic map, which was a paper which was published in Nature. And he realized that you can have very sensitive dependence on the initial condition. This is actually you have this iterative map, and this, according to the control parameter, which is R here, you can have a very regular solution or a very unpredictable one if you are beyond a certain threshold. And this is the geometric construction of the logistic map, and you see that very similar initial condition produce after a few iteration, very different behavior. So, but also driven and dampened pendulum can show similar behavior, and this was really a surprise. I mean, pendula are all around us, and then, as I was saying before, there were a few Russian mathematicians and some also American, Birkhoff and others, among the mathematicians. There was Kolmogorov and others that continued to work on chaos. But then it was rediscovered by a meteorologist, Lorentz, who just by chance, as happens very often, doing some computer calculation and repeating it with an approximation, an initial condition, and obtaining by chance a different evolution, realized that even flows can have this kind of problem. And this was the simple Lorentz model, which is a description, a very simple description of the atmospheric flow. It's actually a Rayleigh-Bernard convection among two planes at different temperature, and you see that this is the attractor, and you don't see. You see here, you don't see it, but there are a lot of points here, red, which after a few iterations are completely spread all over the attractor. Attractor which has a fractal dimension. And another very important thing, it was realized by Feigenbaum in 1978. Feigenbaum was a particle physicist working at Los Alamos, and he was very interested in this kind of simple model with such a complicated dynamics, and he realized that actually it was not just completely noise, there was a precise order, and he, applying the renormalization group technique that were developed for statistical mechanics, he was able to derive these two constants, which you can obtain considering the diameter of the logistic map and these distances here. The two constants, by the way, are correlated, so once you extract one, the other comes immediately. And the very nice thing apart from that is that this kind of behavior is very common everywhere. It was confirmed experimentally in many experiments with lasers, electronics of different kinds, acoustics, chemical reactions, and computer simulation. And the constants that you get are very close to the one that you can calculate analytically, almost analytically. So this was the birth of chaos theory up to the 80s, and of course you can have spatio-temporal chaos, which is turbulence, which is much more complicated. But the important thing is that there are only two ingredients which are important for chaos, to obtain chaos, which are stretching and folding. As soon as you have stretching and folding, you have chaos in your mechanism. And of course, chaos is a regime. Your pendulum can be in a chaotic regime or it can be in a regular regime. So it's not that a system is always chaotic or is always regular. And this is something important to know when you have the observed nature. Well, then fractals. Why fractals? Because fractals were, I say, discovered by Mandelbrot, which was a mathematician, a Belgian mathematician, which realized that actually another thing that was in front of everyone, that nature has not a simple geometry. Is made, I show many examples. The coastlines of, he asked how long was the coastline of Great Britain, and realized that according to the unit that you use, this is longer and longer because it has a fractal dimension. This is the famous Mandelbrot set, but I have no time to speak about it. And he realized that many objects in nature have a scalar invariance and have a finer and finer structure which is very similar and can have also a non-integer dimension. This non-integer dimension is a simple generalization of the usual dimension that we learn at school. Again, I have no time. Of course, this happened in the 70s, but actually many mathematicians knew already these strange sets. One of these was Cantor, but mathematicians loved continuity, so fractal things, complicated things, were a kind of monster. And this Cantor set, I mean, you take away always the 1/3 of the middle of this segment, initial segment, as a fractal dimension which is in between 0 and 1. Then you can have this Koch curve, which is in between 1 and 2, and others, Semplisky gasket. But the important thing is that this kind of mathematical object describe nature. You see there are a lot of leaves, trees, phenomena which have this kind of structures, and also inside us, not only around us. And there is also a reason for that, because when you have a fractal structure, usually you maximize the surface to volume ratio, and this is important in our lungs, in our veins, and so in our neurons, in our brain, and so this is also very important. And another thing is that with simple iterative rules, you can construct this kind of pictures which are very similar to what you observe. Okay, I don't have much time, so let me just close with this. I will not say anything about complexity. If you ask me, I will tell you something. But this is a brief history of deterministic chaos, starting from Poincaré, then a few mathematicians from the United States and Soviet Union, and then again it was rediscovered. Fermi gave important contribution to nonlinear dynamics with the famous FPU system, but I didn't say anything about that. And then fractals, which are strongly related to the Lyapunov exponents, and strange attractors, which were just discovered by Ruel, and then Feigebaum with the logistic mappings, and then many others. Okay, I close here. Don't want to take much more time. Defined like that, like in the formula that in some system you can calculate it analytically, in some system you can calculate it analytically, very simple one. For example, for maps, it's very simple. For the logistic map, in others, I mean, you have to calculate numerically.